Yes, I am Javier Vega. Um, this is uh, my talk. Thank you to the organizers for letting me give this brief exposition about Poisson geometry and non-commutative geometry through what I call quantization processes. So here is the outline of the talk. I'm gonna go through some motivations, then talk about Poisson geometry, after that, go to non-commutative geometry, and hopefully for the end, we are going to grasp the idea of what is quantization and how these theories of mathematics are linked through this quantization process. Okay, so some motivations. The mathematics of quantization are widely inspired by physics, of course. The concept of quantization and quantum systems was born in physics at the beginning of the 20th century. In those times, physics suffered a strong revolution that reached mathematics in different ways. In particular, the mathematics of quantization is an attempt to formalize the process of canonical quantization used by physicists. In pretty much the same fashion, semi-Riemannian geometry is used to rigorously study general relativity. So these mathematics of quantization are for quantum mechanics and quantum physics, what Riemannian and semi-Riemannian geometry are for general relativity, basically. Um, and today, these ideas have its own sense in mathematics and have gave place to new perspectives and techniques to study geometry. Now, let me spend 1 or 2 minutes to tell you a story about physics so we can relate in a more deeper way with the mathematics I'll be displaying. One of the main differences we find in between quantization in physics and quantization in mathematics is exactly the same we can find in between physics and mathematics themselves. So, physics has ontological meaning. It's real. It's in the real world. We can measure it, and mathematics is pure logical. Yes. So, in physics, a quantum system is a system of subatomic particles, basically. Yes. Quantum physics refers to the series of laws and principles that govern the behavior of subatomic particles. In the first time, in the first try when physicists so many years ago, physicists applied all they know of classical mechanics to calculate trajectories and the position of the subatomic particles in such systems, but they enormously failed. In short words, a completely new model proposed by Max Planck to face these problems triumphed in every calculation and is considered the first treatise ever in quantum physics. So the key idea was to handle energy not as a continuous, but as a little package or quanta, as he called it. So it's basically a discretization of what we usually do in physics. It's like the energy spectrum, instead of continuous, make it discrete. So this idea of treat energy as quantum packets solve the problem and open a completely new branch of physics. In addition, one of the main features this new quantum system have is that now you have to treat all classical observables, which are basically real functions, as operators. So uh, this is the key idea to quantize in the canonical sense. Just promote every classical observable to an operator and include the Schrodinger equation, like you would introduce the Newton equation of force in a classical system. So more in detail, these operators act on a Hilbert space. So what we have done is take the algebra of classical observables of a physical system to an algebra of operators in a Hilbert space, resulting in a quantum system. So let me open Poisson geometry. To begin, let's consider an associative algebra with unit A and introduce this bilinear form, which satisfy these three properties. Okay, so basically it's antisymmetric, the Jacobi's identity, and the Leibniz rule. So if you focus on these two properties, the first two, um, you will notice that this is actually the properties of a Lie bracket. So this bilinear form with these three properties is a Poisson bracket. But these two are actually the requirements for a Lie bracket. So you can say that a Poisson bracket is basically a Lie bracket that satisfies Leibniz rule. Yes. By the way, Leibniz rule is also known as a derivation. Yes. Well, then the Poisson algebra is just this pair, an algebra with the bracket. Um, and in particular, the Poisson bracket defined over the functions in a manifold, in the smooth functions, is usually called a Poisson structure. So if you take the smooth functions over a manifold, you take the algebra of these functions and you equip the Poisson bracket, now you have what is called a Poisson manifold. So a manifold equipped with a Poisson structure is called a Poisson manifold. So to this point, we actually have done nothing but introduce language. So what is the main interest at all to give such definitions? Well, the quickest answer, at least for me, is the Hamilton equations. Yes. So property 3, as I was saying, also known as the derivation rule, imply that if we plug a function in this bracket and leave the other entry free, this induces a vector field. So we can define a Hamiltonian vector field with the bracket. Yes. So this vector field is called the Hamiltonian vector field of the Hamiltonian H. Yes. So the canonical example you can find in the literature of quantum geometry and classical mechanics as well is over R2n. Yes, with these coordinates Q1 to Qn, P1 to Pn. So if we define the Poisson bracket using this formula, then the Hamiltonian vector field is this one. And the differential equations induced by this vector field are called the Hamilton equations. So any solution of the Hamilton equation is an integral group of the Hamiltonian vector field, which in physics is interpreted as the trajectories of the particles moving in the space. In addition, we have that for all smooth function, their change, their changes can be written using the bracket, so we can express the Hamilton equation using the bracket as well, which is a remarkable result. And well, another important aspect of the Poisson structure becomes evident when we notice it's possible to define non-degenerate Poisson brackets by this statement, basically. So we can define Poisson brackets through symplectic forms. Just remember that a symplectic form is an antisymmetric non-degenerate 2 form, yes, which equipped to a manifold is a symplectic manifold. So in this sense, we can prove that all symplectic manifolds are actually Poisson. And that's the reason some authors like to say or like to think in Poisson geometry as some kind of generalization of symplectic, because every symplectic manifold is Poisson, but not all Poisson manifolds. Examples. Mm, well, and now let's step on noncommutative geometry. Yes. To begin this section, let me introduce a very important theorem using algebraic topology. And let's start by considering a topological space X. Yes. Well, it's not hard to prove that the set of analytic functions of the topological space over the complex plane in this case satisfy these three statements, these three properties. That it forms a Banach space with the supremum known. It forms a commutative algebra with, using the point-wise product, and it possesses an involution, which in this case is given by the usual conjugation of complex numbers. Well, these forms, uh, this property shows that actually this forms an involutive Banach algebra, also known as star algebra. So let's pay attention to what just happened here. We started with a topological space, and we ended with a star algebra. So we started with topological properties and ended with algebraic properties. So now we are looking for doing kind of the opposite, going in the other direction. So if we change the perspective and we take some sister algebra and look to the set of characters, which are these functions, these set of characters can be promoted to a topological space. We should remember that any algebra, including sister algebras, has an underlying vector space. Then a representation of some group G in V is this function of G over the automorphisms. Basically, invertible operators or the invertible endomorphisms. And thus, a character is the function that assigns elements of the group with elements of the field through this formula, the trace of the representation of G. And this set of characters does admit non-trivial topologies. And it's because of that reason that we say that we can promote it to a topological space. So now we achieve the opposite direction. Begin with an algebraic structure and reach a topological one. And this, in our example, the field is C, the complex numbers. So then it's possible to prove that the set of characters associated to the C-star algebra induced by C, promoted to a topological space, is identified with the original space. So you do not reach any random topological space. You reach the original one you started with. So with, in particular, for this example, we did algebra of analytic functions. Anyway, analytic functions is just like infinite derivative. It has infinite derivatives. This corresponding in between topological spaces and sister algebras is the idea behind the Gelfand duality theorem, which writes as follows. So this pair of functors in between the category of commutative sister algebras and the category of topological complex spaces is an equivalence of categories. By the way, check that this category is the opposite category, which is basically the same one, but with the arrows inverted, with the morphisms inverted. So here, well, this means that basically we can kind of have like a dictionary in between topological properties and algebraic properties. Yes, we can go and come from topology and system algebraic structures. And here I present a table with some properties we can link together. For example, in topology, you can find locally compact topological spaces, and you can identify them with commutative system algebra. Continuous functions, their counterpart is an algebra homomorphism. So compactness with the existence of an identity. And let's stand in topological spaces for a minute. So uh, try to think what is beyond a topological space. How can we go further a topological space? How can we generalize the concept of a topological space? If you ask me, at least for me, it's not easy to think. It's non-trivial, of course. But let's take a look to the in the side of the Reich structures in the commutative sister algebra. How can we go further a sister algebra? How can we reach the next level? Well, it's a commutative sister algebra. If we remove the commutative part, then you have a non-commutative sister algebra. And the question here is, well, if you consider a non-commutative sister algebra, what is their counterpart in the topological sign? What corresponds, what topological structure corresponds to a non-commutative sister algebra? That's basically the heart on the idea behind non-commutative geometry. So this was the brilliant idea that Ellen Coins had of research what kind of topological spaces could be related to non-commutative sister algebras. And for instance, something we can call a non-commutative topological space. As well, it has become common call them quantum groups. And this level, quantum groups, is not by chance, it's not because they wanted it, it actually has its purpose. Well, um, now let's go for quantization. So hopefully, and surely those already initiated in quantum mechanics have already grasped the idea of what is the bridge in between Poisson geometry and non-commutative geometry. Because the example I presented at the beginning of the Poisson structure of Poisson geometry is actually what is used to model classical mechanics. So classical mechanics is basically the algebra of functions in a Poisson manifold. So what happens if you quantize or if you look for the non-commutative counterpart of this Poisson structure, of this classical mechanics? What you find is precisely the algebra of operators of quantum mechanics. So that's what the reason they call it is a quantization. So finding non-commutative spaces is basically a Dirac noticed time after his formulation of quantum mechanics that the algebraic description given by the Poisson brackets over the manifold M is crucial to understand the process of quantization. So he listed a series of um, requirements that any quantization scheme must satisfy. Um, these properties are often called the von Neumann-Dirac axioms for quantization schemes. In particular, I'm going to talk about deformation quantization. Yes, but there are others, for example, geometric quantization. So in this case of deformation, the algebra of functions over the manifold is replaced by the algebra over the commutative, over the ring in this variable H1. And the elements of this algebra are the power series. So the functions in here have this form. And then a deformation is the pair of this algebra together with this product. Is basically the Moyer product. So two very specific examples of this idea of deformation are basically the Clifford algebra, which can be seen as the deformation of the exterior algebra, or the quantization of the exterior algebra, and the Weil algebra, which can be seen as the deformation of the symmetric algebra, or the quantization of the symmetric algebra. So for the final remarks, the starting point of any classical theory of physics is a triplet of the algebra, the bracket, and the Hamiltonian. The algebra being the functions over the manifold. And the starting point in non-commutative geometry is the spectral triple, which is the sister algebra, Hilbert space, and the Dirac operator. So both are linked by a quantization. And as a conclusion, we can say that the formation of the algebra of a smooth function in a Poisson manifold corresponds with a non-commutative space, also called a quantum group. So this is the reason why some authors like to say that, like to talk about quantum geometry, which is just a different name for non-commutative geometry. And well, this is the story I wanted to tell you about. Here are the references. In case you want to check in detail, you can send me a message. I can pass the presentation if needed, so you can check the references more in detail. And well, this is what. Thank you for your time.
Yes, thank you very much. Maybe some questions. Yes, Vladimir has a question.
Yeah, I have a technical remark. Thanks for your talk. Maybe you can just very briefly introduce yourself. Like, where are you? What are you doing?
Oh, well, I'm from Mexico. I actually have not done the PhD yet. I have graduated from the university, and I am looking for places where to continue the master. And so in the beginning of the presentation, you can find email there. So is there if anyone wants to ask something or whatever, and the references are very worth to check. They're really good.
Thank you.
So thank you very much. Maybe some more questions. A second. Please, Alena.
Oh, sorry. I just want to.
Okay.
Sense, yes.
Thank you.